Subscribe to Tech Talks and hit the bell icon to get notifications about coolest and latest engineering technology in the first place.
Hello friends, hope you are fine. In this video, we will see a three-phase front-end converter or active rectifier with space vector PWM. So the input specifications are, it will be having a rated power of 20 kilowatt. The DC voltage will be 700 volt. The minimum DC voltage will be 600 volt. The grid line-to-line voltage RMS, that will be 415 volt. The grid frequency shall be 50 hertz and the switching frequency will be 20 kilohertz. So this is an overall diagram of a active front end. So this is the grid. Okay, so this is 415 volt RMS and 50 hertz. So it is having a resistance and an inductance in series, the grid resistance and grid inductance. So this one is the current sensor, and this one is the inverter. This is the DC bus capacitor, and this is the load. This portion is the controls logic of this converter. We will gradually see into this. This is the MATLAB simulation of this whole block. This is the power circuit. So you can see very well that, and this is the control circuit over here, and this is the observation block. So in the power circuit, you can see this is the supply voltage. So this is the measurement block. It will measure the grid voltage. This is the RL, grid RL. This is the current measurement block. This is the inverter, BSI inverter. This is the capacitor. This is the resistance, and this is also the resistance. This is the load. So we will now explore each of this part one by one, starting from the inverter. Now we will make the VSI or voltage source inverter. For making the voltage source inverter, we require one IGBT, one PWM to go to this here, and these two are the connection port. So first we will place 6 switches over here, 1, 2, and then 3, 4, and 5, 6. Right now we will place the PWM over here. Before placing the PWM, we will connect this part. Okay, so this one. Now this one, the negative points will be connected over here. This will be connected here, and this will be connected over here, and internally they will be connected. Okay, so this is done. Okay, and now we will be putting the voltages over here. So this is VR, and we will make another one. This is our VY, and this is our RYB. This will be B. Now the DC bus voltage we will be placing it over here. So this is the positive DC bus, and we will place another part over here. So this is the negative DC bus. Okay. Now we will be placing the PWM. So we will make, this is PWM 1. So this is for switch 1. This one I will name it as PWM 2, 1 PWM 3, then PWM 4, PWM 5, and then PWM 6. So this is switch number 1, this is switch number 2, this is switch 3, this is switch 4, this is switch 5, and this is switch 6. So this completes our VSI or voltage source inverter. So now we will make a subsystem out of this, and we will rearrange this one. So okay, so this is our the inverter or VSI. We shall now make the power circuit. So for making the power circuit, we require, this is the VSI that we have made earlier, and we require a 3-phase AC source. Okay, so this is a start to ground, and the phase voltage, that is 240 50 hertz, and this is the RL load. So I have put here R grid, so this will be 5 millihenry, 0.005, and this will be 120 microhenry, 120 into 10 to the power -6. Okay, so we will be now placing one by one. First we will place the 3-phase AC source. We will place the measurement block. So A will go to A, B will go to B, and C will go to C. And then we will place the RL load, grid side RL, this is not the load. And after that again we will place the measurement 1, 2, 3, and after that we will place the VSI. This will go to here, B, and this is C. And after that, in the DC side, we will be placing the A series RL branch, series branch, and here we will place a capacitor. Okay. Now we have to measure the current of the load. So we will be placing a current measurement in this load, and this is our load. We will put a resistor over here. For the time being, we will put a resistor of 20 ohm. We can change this value later. Okay, and for the capacitance, now we will place a value of 1200 microfarad. Okay, we will change all this value later accordingly. So this completes our power circuit. Now we will make a certain put certain measuring blocks and other blocks over here. So for that we will first place a go-to block to measure the grid voltage. We will also put a demarks over here, so that we can take this voltages individually. So this is our VR, this will be VB, VRY, and this will be VB. Make it a little longer. VRYB. Similarly, from here we will be measuring the current. This is IRYB, and we will place it over here. And this one we will copy, and we will place it over here and change everything for the current. This will be IR, this will be IY, and this one will be IB. Now for measuring the output voltage, that is the voltage, the capacitance, output capacitance, we will place a voltage measurement block over here. So this one will be measuring our VDC voltage, and this one will be measuring our IDC current. Okay. This is not required, we have already used it. And this block is may be required or may not be required. It is optional actually. So I will put another resistance over here. And this is an ideal switch. I will just put a step function over here, but I will place all these values, initial value 0 and final value also 0. That means it is closed all time. That is open all time. So that means this is actually open circuited. So till here is our power circuit block. So again, once again, so this is our three-phase grid. Okay, this is the measurement block. This is the RL of the grid side. This is again the measurement block. This is the VSI inverter that we have made, and after that a capacitance and the load. These two are the DC bus voltage and current measurement. This part is optional, and this one will measure the grid side voltage, and this part will measure the grid side current. We have made the power circuit block. Now we will be making the logic circuit block. So for making the logic circuit block, we will first make the PLL, that is the phase lock loop. Now the phase lock loop, in phase lock loop what we will do, we will take the VRYB voltage, we will be transforming it to alpha beta. Then from alpha beta we will be taking two low pass filter with a cutoff frequency of 50 Hz, and then we will be normalizing it, and we will be getting cos theta and sin theta. So now let us do it in MATLAB. Okay, so we will take a ABC to alpha beta block. So I will make VR, VY and VV. This is RY and B. I need a demarc. Sorry, I need a marks over here. So I will be connecting this parts BR, BY and BB. Now I will be going this one to B ABC to B alpha beta. We will be taking a demarcs over here. So V alpha will be coming over here, V beta will be coming over here. Need 2, and I will be naming it as alpha and beta. Now this alpha and beta what I have created over there will be placed over here. This is V alpha beta, and this is the demarks. Here I have put 2 LPFs. Okay, so this is the numerator and this is the 2 pi f. Similarly, the second LPF, likewise here. So here I have written a function of now this is x, actually this is x. I will name it as x, and this one is y. And this one is y. Okay, so the function one here is x divided by square root of x square plus y square. So that is what is written over here. And similarly here this is y divided by square root of x square plus y square. Okay, so this will give me the sine and this will give me the cos. So sine by cos will be tan, and this is inverse of tan. Now I will be putting it in a mod, the modulation. Okay, and I will be putting 2 pi over here, and this will give me omega t. Now this omega t I will be using over here, omega t. Now from alpha beta I will be making dq. So this is my alpha beta and this will be omega t, and this will be my vd vq. So I will be again taking this block, make it 3. Sorry, I will not be taking this block, I will be taking this block. So this is VD, this will be VQ, and this I will be leaving alone. And now the similar thing I will be doing with this for the current one also. So I will be copying this whole part. This is IR, this is IY, and this is IB. And this omega t, this is omega t. The same omega t will be used over here, and this part I will be again copying it, and I will rename it as ID and IQ. Now I will be terminating the points that is not used. I will use this terminator and place it over here. This is not required, and also I will be placing one over here. So this is actually my alpha 2 or beta ABC2 DQ, and with the PLL part. So after we have made the power circuit and the parallel logic, now we will be doing the logic circuit of this block. So for that we will subtract the VDC from VDC reference and the VDC, and there is a PI controller with a limiter, and it will generate the IQ reference. We will subtract this one from the IQ, actual IQ, and again a PI block, and we will then adjust the feed forward terms or the cross reference terms. So this will give us the VD, VD and VQ. So here we will get VQ, and likewise here we will get VD reference, that is to be transferred to DQ to ABC. Now here we will do the same thing. We will put the D-axis current 0. So two highlights, the key highlights are over here. Here I am considering the active power is been active power is transferred from a leading voltage to a lagging voltage, and the active power is transferred from a higher voltage to a lower voltage. Here we are considering the Q axis as the active power axis and D axis as the reactive power axis. So you can very well see that this Q axis, so this is the active power axis, and D axis is the reactive power axis. So in reactive power we are keeping this one as 0. So moving to the MATLAB. So now we will make the Q axis PI controller. So this is our VD, what we are VD reference. So I will be putting VDC reference. So I have taken a step, and I will give this step voltage from 600 to 700 volt, and it will be a jump at 1 second. And from here the actual VDC will be subtracted, then it will be going to a PI block. So I will put an arbitrary value over here. Let us put 2 and 10. So these values are arbitrary value. We will change it later as per our calculation. Now here this is the VD reference. Now here after the PI we are generating an IQ reference. Now this IQ reference will be then subtracted from the IQ. So this is our IQ reference. Here also we will be using a PI controller and put an arbitrary value of 2 and 10. We will let us change this value, and then we will adjust the cross terms. The cross terms is over here. Here it is 2 pi omega. Omega is 50, and L grid. This is the L grid, and multiplied by ID. So after that, whatever we have got, we will add VD to it. VQ to it. We will add VQ to it. So here we are getting the modulation function. To get the modulation function, we will be dividing this one with VDC by 2. So this is VDC by 2. We will be dividing the whole by whole with this one. So here we will be getting VD. Similarly, we will do the same thing for the IQ. One thing over here is that we will add a small LPF block with a 100 Hertz frequency in VDC, so that it ramps up very slowly. So we will make a copy from this part, and we will put it over here. So this one we will put a constant. So this is our D axis. We will put it 0. We will put it 0, and similarly now we will subtract ID. Now there is a PI controller. This is the D axis current controller. So here it will be ID. ID. Here it will be omega L grid, and here it will be IQ. Here we will be adding VD. These are this is the cross coupling term or the feed forward term, and the other things are constant. Only thing is that here there will be a sign change of minus and minus. This comes from the equation, mathematical equation. Okay. Now here this ends our control logic. From here we are getting VD and VQ. Okay. Made the controller for the D axis and the Q axis. Now we will be making them to the BABC. So for that already I have made a block. So this is VD, so I will be putting it over here, and this is VQ, so I will be putting it over here. So this is 0, VD 0. This is the omega t that we have created from the unit vector generation. This is the DQ to ABC block, and after that this is the VA reference, VB reference, VC reference, and we have put it to a block, that is the VA reference, VB reference. To here, if you give a sine wave, we will get the SVPWM from here, and that one we will be comparing with a triangular wave. So the triangular wave frequency we will be adjusting over here. Okay. So this is the switching frequency, and this is half of that switching frequency, and here it is go from -1, 1 and -1, and from here the pulse switch for 1 and 2, and then 3, 4, and then 5, 6 it will come out. So it will be pulse width 1, 2, 3, 4 and 5, 6. Okay. Now this one will go to 1 and this one will go to 4 likewise. Now we will do the programming to find out the KPKI value and the capacitor values. So for that, this is the power rating. So this is 20 kilowatt. This is the VDC, that is 700 volt. This is the VDC means 600 volt. This is the VLL 415 volt. This is a grid frequency 50 hertz, switching frequency 20 kilohertz, and the delta V VDC, that is I have taken 3% of the VDC. So this will be coming around 21 volt. Okay. Now we will be running this program. Okay, and you can see every values over here. Okay. So you see that this is the capacitance value, that it is telling that you should put this value in capacitance, that is 22300 microfarad. So I will be taking a little more than that one. I will be taking this one as 3000 microfarad, and I will be running this program again. Now this program is running with 30 microfarad. Okay. Now here you see that it will be giving me the PI controller value. So this is the I of voltage, and this one is the proportional for the voltage controller, and these two KI and KP. So these are the values of PI for the current. Now we will be placing all values in that program. Also you can notice the R grid is 5 milliohm and L grid, that is 120 microhenry. Okay. Now in MATLAB we will be placing all those values one by one. So here this is the RL. So I will be placing here at R grid. This is R grid, and here I will be placing L grid, and here nothing to change except this one. So here I will be placing it as CDC. Why CDC? Because here my capacitance value is stored in C underscore DC. So C underscore DC. So this is okay. Now here nothing to change. Now only in the controller block we will change those values. Yes, this is the controller block. So first we will change this value in the Q axis. So this is the PI controller of the voltage loop. So here I will be putting see over here. I will be putting KP underscore wall and KI underscore wall. So this will be KP underscore wall, and this is KI underscore wall. Wall is for voltage, and similarly here this is for the current loop. Here I will be only putting KP and KI. Here also I will be putting KP and KI. All values it will be calculating automatically. And in cross coupling terms, so here L grid is already there. I'm just checking it. Here also L grid is there. Okay. And moving on, this is all okay. Now we will be going to the result section. So now we will be exploring the result. So for that one, first we will be putting the model. So here I have used fixed step solver, okay. And this is ODE5 dormant price, and the step size I have kept as 25 microsecond. Okay, the same we will put it in this GUI. Okay, so this is the power circuit. So the resistance that I have put over here is 24.5 ohm. Okay. And this is the controller block. This is the controller block, like the previous that we have made, and this is the observation block. Okay, now here we will give the voltage reference. We will give the voltage reference from 600 to 700 volt, and we will give it as 0.5. That is at 0.5 it will be moving from 600 to 700 volt, and I will put this one to 1. I will save this one, and I will simulate this one. Okay, the simulation is done. Now let us go through the result. So this is the VDC reference, and this is the VDC. So this is the VDC reference and VDC. So in the third of this one, you can see that this is our voltage, and this is the current. At 0.5 you can see a spike over here, and here at this point of time you can see that the voltage is closely following the reference voltage. Okay, and this one. So here this upper point is the DC voltage. So first we have set at 600 volt, so it is following 600 volt. At 0.5 second it is moving to 700 volt, and this is the current, IDC current. So it is taking around 24.6 ampere, and at 0.5, that is at 700, so it is taking around 28.6 ampere current. And in this block there is a multiplication of VDC and IDC, that is the output. So our output shall be 20 kilowatt at 700 volt, and this is the input measurement, that is the VRYB, that is the voltage over here. and this is the current. So these two multiplication instantaneously, so that is done. P is the active power over here. So let us see. So you can see that at 700 volts, so this is at 700 volt, so we are going to 2, that is into 10 to the power minus 4, so that is 20 kilowatt. So our rating of the converter was 20 kilowatt, so at 700 volt we are reaching 20 kilowatt. Okay, and this is the active power. So whenever there is a jump in the voltage, so we are drawing more active power. However, our reactive power component is constant, that is no reactive power is drawn. That is because we have kept the reactive power component, that is this one as 0, that is ID, this one as 0. Right? So this model is working well. Thank you for watching.
Comment below about how you like this video. Check out the links in the description box about more such videos. Do click the like button if you like the video. If you are new to this channel, subscribe Tech Talks and don't forget to hit the bell icon.